The next presentation, Pretreatment and Surface Preparation for Wet Paint Systems, will be presented by Gail Siemens. Gail is the Regional Sales Manager and Aerospace Development Manager for Fremont Industries Incorporated in Shakopee, Minnesota. Gail has had over 16 years in surface cleaning and pre-paint treatment. He's a member of the American Electroplaters and Surface Finishers Society Incorporated and the Society of Manufacturing Engineers. Welcome, Gail.
Thank you, Cam. Good morning. Environmental concerns and regulations have mandated that increased attention be paid to the methods used in a preparation of surfaces to be painted. The earliest methods of surface preparation involve simple solvent wiping to remove gross amounts of oils, greases, and shop soils from the parts. This gradually led to the development of vapor degreasing. With solvent-based paints, a minute amount of oily residue was easily dispersed by the solvent in the paint, and good paint adhesion was often achieved. However, underfilm corrosion protection was poor. The need for better corrosion protection led to the development of alkaline cleaning to remove organic soils and acidic conversion coating of metal substrates to achieve 1, a water break-free clean part, and 2, an acidified conversion coating to convert the metal surface to a less conductive state, which helps to inhibit the spread of underfilm corrosion. The result is a combination of good paint adhesion and improved underfilm corrosion resistance. The challenge of the past decade has been to develop conversion coating and sealing processes that are environmentally acceptable. For many years, the use of chromate conversion coatings on non-ferrous metals and chrome seal rinses of phosphate coatings on ferrous metals has provided the ultimate corrosion protection for pre-paint systems. Many specifications still mandate the use of chrome. This will have to change. The only question is, how soon? The metal finishing industry is faced with the dilemma of increased quality requirements of the world-class marketplace versus the demand to protect our environment from the dangers of heavy metal waste. In the non-ferrous metal industries, non-chrome processes have been developed that rival the corrosion protection of chromates when the part is subsequently painted. For unpainted parts, chrome is still the standard. In the iron phosphate conversion coating of ferrous metals, while many advances have been made in improving the phosphate coatings to provide appliance-grade phosphate substrates, non-chrome seal rinses provide a varying degree of corrosion protection. Particular attention needs to be paid to the compatibility of the paint to the seal rinse. Some of the non-chrome seal rinse compounds have shown to be quite paint-specific. You also need to review material safety data sheets to assure that other restricted materials have not been substituted for chrome. While none of the available non-chrome seal rinses can compare across the board to chrome for underfilm corrosion protection, deionized water has shown to be a good alternative in many cases. We would encourage the testing of deionized water whenever you are evaluating your pretreatment process. In the pretreatment and surface preparation, there are several steps that can be taken to improve the performance of your system while lessening the environmental control costs associated with waste disposal. There are many different types of soils used in a manufacturing facility. We often overlook or assume that all soils will be easily cleaned. The cleaning operation would be less difficult if we understood more completely all the individual soils are generally shop dirt, smut, oil, metal chips, and drying, stamping, and buffing compounds. Upon completion of a soil audit and the determination of a suitable cleaner, every effort should be made not to introduce new soils without pre-testing. Soils can be classified as organic soils, which are oily, waxy films such as mill oils, rust inhibitors, coolants, lubricants, and drying compounds. These are classified as organic solids. Alkaline cleaners clean organic soils. The other type of soils are inorganic soils. They would include rust, smut, heat scale, and inorganic particulate, abrasives, flux, and shop dust. These inorganic soils are most easily cleaned by acidic cleaners. Acidic cleaners clean inorganic soils. All soils fall into three basic categories, which are very difficult soils, such as chlorinated lubricants, sulfurized lubricants, heavy-duty rust-inhibiting compounds, thick honey oils, buffing compounds and stearates, and oxidized soils. The moderate degree soils would be fatty oils, whey oils, heavy-duty hydraulic oils, mill oils, lapping compounds, water-displacing rust inhibitors, and those type of oils. Light degree soils, which are more easily cleaned, would include soluble oil, cutting fluids, synthetic cutting fluids, spindle oils, lightweight machine oils, mill oils, water-soluble rust inhibitors, and vanishing oils. The very difficult soils tend to be heat sensitive. Soils falling into the naphthenic, paraffinic, chlorinated paraffin blends, or those containing waxes, are generally heat sensitive to some degree. When you encounter this type of soil, it limits the variable of temperature. A heat-sensitive soil of, let's say, 160 degrees Fahrenheit requires you to adjust your heat cleaning bath temperature upwards. Specifically formulated low-temperature cleaners rely on both soil displacement and slight emulsification. The blend of detergent systems built into the low-temperature cleaners are designed to reduce surface temperature tension at the soil-metal interface. This unique factor enables us to remove soils sensitive to heat at a lower temperature, lower than the melting point of the waxes of that soil. This fact also produces less contamination if properly skimmed, resulting in longer cleaning tank life. Acidic nature soils with an acidic nature such as some of the soluble oils and soils containing fatty acids can create severe foaming problems. The reason being that under heat and in an alkaline system, these fatty acids convert to soap, which overloads the defoaming system when the soil reaches a saturation that exceeds the anti-foam capabilities of the cleaner in solution. Fatty acids plus alkali plus agitation and heat equals soap and foam. When the incoming soil load reaches the particular cleaner's ability to control, this saturation point generally reduces the tank life drastically. If you should encounter these types of soils, you have three alternatives. The first would be to increase the concentration of the cleaner. By increasing the concentration, you increase the defoamer system to combat the increase in soil load. The second alternative would be to raise the temperature of the cleaning bath. By increasing the temperature, you help to increase the insolubility of the defoamer. This causes faster foam deactivation. The third alternative would be adding more defoamer. The use of a defoamer will combat foam by increasing the ability to control foam at greater concentration. Another step, while not the most advantageous, would be to dump and recharge. That is the last resort. Fresh solution adds additional foam control properties to the bath and obviously will increase the cleaning ability of the bath. However, the most advantageous change you should make would be to change the soil. Evaluate alternatives for that particular soil. Once you've conducted a soil audit, you should then conduct a substrate audit for your plant. The composition or chemistry of the base metal is one of the key limiting factors to cleaner choice. The cleaner must be chosen so as to be compatible with the metal being processed. In multi-metal cleaning lines, non-ferrous metals are typically the limiting factor. With these metals, it is important to choose a cleaner which either does not attack or over-etch the metal, and where the attack is controllable or desirable. A common mistake by both chemical vendors and manufacturers is that when a base metal audit is made for cleaner selection, but not done completely. Yes, it's acknowledged that this line is multi-metal, but no, not all alloys were pre-screened. Most aluminum and zinc alloys with slightly different alloy content can vary widely in the ability to withstand either alkaline or acidic cleaner attack. In some cases, where minute etch is desirable, slightly more or slightly less is unacceptable. The four basic substrate classifications would be the ferrous metals or iron-bearing metals, which would be cold-rolled steel, hot-rolled steel, stainless steel, and ferrous castings. The typical non-ferrous metals would include aluminum, sheet, coil, and castings or extrusions, zinc castings, and galvanized. Turnplate and zinc plate would also fall in that category. The third basic classification would be the yellow metals, which are copper and brass. And fourth, and the one that causes the most problems in cleaning and pretreatment lines, would be the mixed metals, which are combinations of the above. The selection of chemicals for cleaning and phosphating or other conversion coating can result in the presence of unacceptable levels of zinc, aluminum, or other sensitive metals in your waste stream. The use of a heavily chelated alkaline cleaner would result in increased difficulty in removing these metals from your waste stream. Consider counterflowing rinse stages. For example, in a 5-stage iron phosphate pretreatment washer, counterflow stage 4, which is the rinse following the iron phosphate, into stage 2, which is the rinse following the alkaline cleaner. In this arrangement, all of the freshwater makeup is fed into stage 4. The stage 4 overflow serves as the makeup and overflow for stage 2. The result is a 50% reduction in freshwater usage, plus the use of slightly acidic stage 4 water to help reduce alkalinity in stage 2. As was mentioned earlier, keep tramp oils skimmed off cleaner and rinse stages. This prevents oils from being redeposited on the part and helps prolong bath life. Consider filtration of the cleaning and phosphating baths to reduce sludge and metal fines. This helps keep risers and nozzles from plugging, and it extends the bath life. In summary, be realistic in the evaluation of your capabilities and needs. You can make dramatic improvements in quality without any sacrifice in environmental concerns. Audit your entire operation to find opportunities for improvement. Look at the mechanical end of your pretreatment system as well as the chemical. Provide a clean, uniform, conversion-coated part to your paint system, and quality will never suffer. Do all this in a responsible manner, and our environment will benefit.